Well, g'day, flatties and reality defenders. This is Critical Think from Down Under. Thank you, very kind. Well, today we're going to talk about how the globe is confirmed by the weight change measurements done during the final experiment. Now, I'll be talking not just about the experiment, but a little bit about the final experiment. So in that context, I'll be having a bit of a rant at the beginning, and then I'll present the method, the results, a little bit of background of the experiment, and we'll have a little bit of fun at the end. So here we go. Now, what irks me a little bit recently is this false flat earth narrative, in that globers blindly believe what they are taught. This is absurd, and people who say this have no idea. They've never been through the education system. They don't know what it takes to be a professional. They don't know that we do not blindly believe what we are taught. Now, this is highly insulting to all those highly trained professionals who work cleverly, hard and honestly to improve everyone's lives, including the lives of the flat earthers. Now, flat earthers, if you're really serious about your religion, you should throw away your mobile phone. Don't use GPS, because all these things are provided to you by these people who you say are indoctrinated liars. So to be true to your cause, you should not use your mobile phone or your GPS. Now, this experiment I'm going to describe today, it falsifies this following statement, that globers blindly believe what they are taught, and I'll explain how it does that. This experiment is about taking real-world measurements and to test the truth of what we are taught, not just to blindly accept. And recently, I just want to say, Neil deGrasse Tyson publicly stated that weight does not change at different latitudes. He is, of course, wrong, and I provide evidence that this so-called mainstream opinion is wrong. So you see, us globers don't blindly accept from the mainstream. We have our own thoughts, our own experiments, and we independently verify. Now, I'm not just some random dude on the internet, as some people have described. I am a qualified engineer with a master's degree. I've got 50 years of experience working as a respected professional engineer. Now, just because I don't appear on mainstream doesn't mean I don't know what I'm talking about. I have performed this experiment as a personal project of mine on various occasions since 2019. Now, the idea for this experiment first came from a YouTuber called Wolfie6020, and most of you will already know him. Now, if you haven't seen the videos on his channel, you should go there. Some of them are old, like this one is 7 years old, but the content doesn't get old. Wolfie6020 produces some brilliant content. So if you're at all thinking that the earth may be flat, I suggest you go and watch this content, and that should help you make the correct decision. Now, Wolfie did this experiment, and I'll just play a little bit from the intro to this video.
So one of the comments I see quite often on flat earth discussions is, how can you prove we're on a spinning ball? How can we actually prove that? I'm just going to talk about that for a moment, and just consider the fact that if we are actually on a spinning ball that is rotating like this, that is moving 1,040 miles per hour at the equator, there should be a measurable difference in the weight of objects when they are measured at the equator compared to when they are measured at a higher latitude. And by higher latitude, I mean higher south latitude value or higher north latitude value. And let's just take Perth, for example. If I measured the weight of an object in Perth, and then I measured the weight of it again in Singapore using the same set of scales, an accurate pair of the scales, and using exactly the same weight, there should be a noticeable difference. And that would be evidence, I won't say proof in this case, but that would be strong evidence that supports the fact that we're on a spinning ball. Now,
So you see what he said there? He said if, not accepting this blindly. He says if the Earth was a spinning ball, we would see this. So that's not accepting blindly. That's testing reality. That's testing the hypothesis. Now, a little bit of theory, just quickly. I've done this before, but some people ask for a bit of a recap on this. So the Earth is not exactly a circle, and we have to take that into account. And I should say not exactly a sphere. We have to take that into account in all the calculations, and we follow, for the purpose of this experiment, in the final experiment, we follow the WGS 84 model. So the forces involved here at the equator, you have 9.8142 newtons pulling you towards the centre of the Earth, and the so-called I will fly off because I'm spinning at 1,000 mile per hour force is like a small fraction of that. It is 0.0339 newtons. So the flinging off force is very small compared to the force holding you down to the surface. Now, as we move away from the equator, the direction of the centrifugal force gets not perpendicular to the surface anymore. So there is a component of the centrifugal force that is perpendicular to the surface and in the same direction of gravity. And this is, in this case, that example I've got here at 30 degrees is 0.0255 newtons. And this will cause a heavier weight there because that flinging off force is less, and the speed gets less too. So as you go towards the pole, there's almost no centrifugal force here. You're also a little bit closer to the centre of the Earth, so you will weigh more at the pole than you will at the equator. So that's the principle of this. Now we have, if it was a rotating perfect sphere, we would use these equations, but it's not a perfect sphere. It's oblate because it is rotating, and there will be more videos on this topic to come. So this is the WGS 84 equation. Now, Walter Bislins has documented this on his website, and I'll put a link to that page. Walter Bislin, one very smart guy who's done a lot of work. His website is full of useful information. Now, this is the equation I use to predict what would be the weight at any particular location. Now note, this is the theory, but I am going to go out and measure it to verify whether this equation is correct or not correct. This is not blindly believing. This is, let's check this to see if it's right. Now, I've also been accused of not following the scientific method. This is what flat earthers say when they've got nothing else to say and they don't understand the scientific method. But basically, we've got here, in general, we look for a new law by the following process. First, we guess it, which is the hypothesis. So we've got a hypothesis WGS 84. Then we compute the consequences. So in this case, we're going to compute what something should weigh. That's a consequence of the WGS 84 gravity model. And then we compare the computation results to nature. That is, we go out and measure and see what nature tells us. So we compare it directly with the observation to see if it works. If what we predict disagrees with what we measure in an experiment, then the hypothesis is wrong. So the globe is wrong if the weight does not agree. And then that's a simple statement, and that is the key to the science. So I'm following the scientific method here. So to the final experiment. Now, I've been doing measurements like this since 2019. Now, I've got better and better at it as the years go by. I've found a good set of scales, a good electronic scale. I know how to avoid some of the pitfalls. And so this final experiment was only going to happen once. I had to make sure that I was totally prepared for this event, and such. I concentrated solely on this because it was far too important to get it wrong. So I've got some videos on my channel where I did some, you can see all my prior measurements. I did a couple of test runs with 2 different scales, and I was trying to decide which would be my best scale to bring on the final experiment. So this is where we started in Redcliffe, and we flew to Sydney, and we'll just flip over to Google Earth, and here's the flight I took to Sydney, and then we flew a QF-27 across the Southern Pacific, crossing over New Zealand. We'll be documenting this flight in due time, and ended up in Santiago. Now, some of you are probably a little bit confused by the orientation. We'll try and move it a little bit. And then Santiago, flew to Punta Arenas, and then flew to Union Glacier. Now, I have never been to Santiago, Punta Arenas or Union Glacier prior to the final experiment. I have been to Sydney. I, of course, been home. So in these places here, I've never been there. I looked up on Google and worked out what were the approximate latitude and elevations. Now, I didn't get them exactly right, but I measured them wherever I can once I got there. But from these very close approximations, I was able to make a prediction as to what my scale should weigh when I weigh at these locations. I weigh my standard mass. So I've documented those predictions, and they popped up. We put them on MC Toon's final experiment predictions page. So here they are. These are the original. These are the original predictions, and we gave a flat Earth prediction as no change. This is based mainly on the principle that a certain flat earther said was that a kilogram is a kilogram everywhere on the Earth. So there's no hypothesis for why the weight should change on a flat Earth. There's no reason, no hypothesis, nothing put forward from the flat earthers. No prediction really, but that's the prediction that we've got, is that nothing changes because there's nothing else put forward. And no flat earther has actually disputed any of this. I brought 3 scales on the trip. Now, I did not recalibrate this scale, which is my main scale, my most accurate scale. So I had taken this scale to Thailand in July this year. And when it was calibrated, it was 1000.01 was the reading. And it was reading 1000.02. And it read 1000.01 sometimes as well. But this is my last reading before I left. Scale is the same calibration as when I went to Thailand. I did recalibrate my El Cheapo scale. So this one has been handed over to MC Toon, and we'll analyse that later. And I brought my backup scale. So this is my second best scale. I took that to Thailand in September, October, and I tested it, how accurate it was and how stable it was. So this scale I packed in my checked baggage in case something went wrong and I lost this one or broke it or something, then I had a backup scale in case. So that one went in checked, and this one was carry on, and this one was carry on. Now, I videoed most of the weight measurements along the way, and those are on my channel. And I won't play them all because I didn't want this video to go on forever. I could go on for a long time, but maybe I'll expand some pieces in the future. But this is the most important measurement, was the one that I made at Union Glacier. Just remember that I hadn't been there, hadn't been here. I made a prediction, which was, in this case, 1003.80 grams, and let's see how that goes. The measurement. So we're going to go ahead with the best scale I got, which the prediction is 1003.80. So down there outside it was 1003. We weighed it around about 76. So in here, a little bit more stable environment, it's a little bit more 1000, but it's still 1003 is settled down to 0.82, which is 0.02 of a gram from what was predicted. So there you have it. I used the hypothesis about the globe model, about what something should weigh, to make a prediction. I went to the location and it weighed pretty much the same. Now I made another measurement out at the camp, the special camp that we were at. So in both cases, the elevation above sea level was different. So I have since modified the predictions based on the actual elevations measured, and it's still very, very close, and this one is in fact closer. So the results then I've plotted in my spreadsheet. I've got set up with all the formulas. So in this graph down the lower left, the green line is what I measured, the red line is the globe prediction. Now remember, the globe prediction includes both curvature and rotation, so none of this prediction could be made without taking into account curvature and rotation. I mean, had someone try to tell me that a globe has no curvature, really, there's some very silly stuff going on. Now, some people ask me, they always ask about temperature and pressure, and some people ask me to measure the pressure. And I still don't know why I'm measuring this pressure, but there you go, that's the weight versus pressure. You can see that there's no correlation, and I'm still waiting for some kind of prediction to plot on that graph. I don't have it. I don't know what the expected result is. Nobody can give it to me. And so that currently is useless, proves nothing. As you can see, there's no correlation and there's no prediction. And on the other hand, I've got my independent variables identified, and I've plotted my result against the expected based on my independent variables, and I get a very strong correlation. Now you can say things like pressure, temperature, magnetism, whatever, but you have to say also how much does that affect the weight. And I've already got my correlation here, so I can pretty much guarantee that the effects of temperature and pressure and all that are not going to be significant. If they were significant, you'd see a lot of variation in this graph. So this is what I do. I got a way of normalizing the results. So because they're at different elevations and that, they each measurement I adjust it in terms of scaling. I scale it down to a standard elevation so that I can plot it on this graph. And so the prediction line is this green line. And as you can see, all the measurements are very good. This is probably my best measurement to date. No, it's not probably, it is. And then I've combined that with measurements I've done in the northern hemisphere. So we've got northern hemisphere and southern hemisphere measurements. We've got my latitude was 27 where I started. So I've got lower latitudes and higher latitudes. And all these measurements were done with the same calibration on the scale. And so as you can see, it fits very, very good. Globe confirmed. Now, the way we determine how good a fit this is, how much does the globe model explain the variations in weight, because the weight does vary. So how is this explained with the globe model? We've got a statistical measure called coefficient of determination, or R squared. So I've worked that out for all of my results. So I've shown here for my final experiment, which I've got 10 points. Now, it's so close to 100 within 1 decimal point. So the WGS 84 model explains 100% of the variation. So the weight varies. It's not explained by temperature. It's not explained by pressure. It's not explained by flatness. It's 100% explained by the WGS 84 globe model, a rotating oblate spheroid. I've also collected data over the years, so not just my own data, but other people's data, but mostly my own data. I've got 138 data points now. And they are normalized data points because some people use different weights and certainly different elevations. But I've normalized it to one elevation and one weight, and then I run them through the analysis. And for 138 data points, the WGS model explains 99.3% of the variation. So this is, anybody who understands the statistics of this is so powerful, right? There is no other valid explanation that has been put forward that can explain this weight difference. So there we have, last time I did a video like this, I plotted all my existing points and I've put the predictions there on the graph there. And then this is the data after taking the measurements, and they are in the exact spot where the prediction was. So I'd call that, the final experiment, a success in the terms of the weight measurement. It matches the globe pretty much perfectly, and the flat Earth is falsified. So, of course, this was all very expensive. Our donations are still open. Thank you to all those people who have generously given, and I would appreciate more donations to help cover the cost of this. Now, those of you who have followed this experiment through the ages, you know that I do, in fact, pretty much make a lot of fun of Phuket Word here, because he said the experiment hasn't been done. And I know you're watching, Nick, because you've put this up on Twitter. Flat Earth is obviously reality. Yeah, okay, whatever you say, dude. But globe believers love to claim that weight predictably changes with latitude. I wonder which particular globe proponent loves to claim that. Not me. Yes, I think it's me, because I measured, I don't claim. I measure. But then he goes on and he says, but even professional scale makers cannot prove this globe assumption. And he points to a video that he did many years ago about the gnome experiment. Now, the gnome experiment was a marketing exercise. The professional scale makers, maybe they professionally make their scales, of course, but the experiment itself was uncontrolled. It was a marketing exercise. It was performed in uncontrolled conditions. Just the scales were just mailed around the world, and random people weighed using the scale. And such a higgledy-piggledy thing, the results are useless because it was not controlled. So Nick here is trying to say that, the professionals have done it, and look, they couldn't even prove the globe. Just a minute. The professionals are here. Nick, here. Hello. I'm a professional, and I've done the experiment correctly. And you know that because you've seen my videos, otherwise you wouldn't have posted this. And so I still don't get a reply from you here. But Nick, look, you don't let your ego get the better of you, okay? It's okay. I will stop making fun of you. You just come to my channel and admit that I've done the experiment, that the experiment certainly confirms the globe and falsifies the flat earth. Now, you don't have to go quite that far, but you can at least acknowledge that I've done the experiment, done the calculations, and the reality of the globe is confirmed with this experiment. So don't be shy. I don't block flat earthers in general, just the most obnoxious ones that contribute just hate to the discussion rather than something useful. So, you know, sometimes you're wrong. Sometimes you're wrong, Nick, and don't let your ego get in the way of admitting that you were wrong on this one. So let's then see, we'll remind ourselves what Phuket Word has to say about this.
Goes on about the difference in the weight of things at the equator compared to other places in the earth. Have you actually gone and measured it? Have you ever done it?
Yes.
We understand that in the model, based on the spin and centrifugals, centripetal whatever forces, that's the result that you can calculate based on your model.
We did.
But has anyone actually gone and measured this so-called difference? Has anyone actually measured that a kilogram weighed in somewhere up north is any different to a kilogram weighed on the equator?
Yes.
Has anyone actually gone and done that?
Yes.
No, they have not.
Ooh.
A kilogram is a kilogram wherever you are on the earth.
But I've just shown through experiment that that's not true. A kilogram is not a kilogram anywhere on Earth.